Hello, in this video, we are going to take a look at things we can now do with power series now that we have power series. So first, we can combine power series. Power series, going back to that first video, is ultimately an infinite polynomial. So if we have an infinite polynomial, we can add them together, we can subtract them, we can compose something inside a infinite polynomial. We can do a lot of things. So that is exactly what these sections or this theorem here is saying. So suppose we have a power series c sub k x to the k and d sub k x to the k that converge to f of x and g of x respectively. Again, we'll see a little bit more about these functions that we can converge to, but in the first video, we learned the property that the series k sub 0 to infinity of x to the k converges to 1 over 1 minus x on the interval -1 to 1. We saw that because of geometric series. And so this idea of a series converging to a function is what is being referenced here. And suppose they have some interval I that they are converging on. Here would be our interval. Then we have the sum and difference rule that the power series of the sum of c sub k plus or minus d sub k, we could be either adding or we could be subtracting, times x to the k, will converge f of x to f of x plus or minus g of x on that interval I. So like if I took this series and added it twice, well, very basic to see, the sum k sub equals 0 to infinity of 1 of x to the k plus x to the k, or 2x to the k, would be equal to 1 over 1 minus x plus 1 over 1 minus x, or 2 over 1 minus x on the interval -1 to 1. We could add them together, and it doesn't have to be the same series twice. This is just the series we know. So we can add two series together, and it would be just adding the coefficients. We can also multiply by a power. So suppose m is an integer such that k plus m is greater than or equal to 0. For all terms of the power series. Then the series x to the m, or if I take x to the m and multiply it by our series, c sub k x to the k, this is the same as the series c sub k x to the k plus n. So I can multiply a power in and combine exponents. This series will converge to x to the m f of x, because x to the c, k, x to the k converges to f of x. For all x not equal to 0 in I, and it will converge to the limit as x goes to 0 of x to the m times f of x when x equals 0. So the interval stays the same. What it converges to, we just have to check that that point of x equals 0. Because yes, we did just multiply by some zeros, but that doesn't mean we didn't have a whole that ended up getting canceled out. So there might be something with that limit to worry about, but in general, the interval is what we really care about, and the interval stays the same. And then the last thing is we can compose, and this is the one we're going to deal with the most. So knowing we can multiply by a power and knowing that we have this sum and difference property is great, and we're going to use it, but the biggest one we're going to use is this composition. And it says, if h of x equals b times x to the m, where m is a positive integer, and b is not 0, then the series c sub k h of x to the k converges to f of h of x for all x such that h of x is in I. Few things that this means. This is just taking h of x and putting it into the place of x. Because we had the power series c sub k x to the k, and we've just taken a function and put it inside. So just a term with a power as the function, but it is still just composing a function inside by putting that function in the place of x. Second thing is that the interval is potentially going to change. But the endpoints won't. And we will see what this last part of this theorem is saying in the examples. But essentially, instead of saying x is between, say, -3 and 3, suppose that was our interval of convergence. Then, when we compose, we will be actually looking at -3 is less than h of x is less than 3. Meaning this function could change that -3 and 3, but it's not going to change the inequalities of the less thans. So then we'd have that. So interval might change, but the endpoints won't. So let's take a look at a couple examples. Suppose we have the series 1 over 1 minus x is equal to k equals 0 to infinity x to the k. We saw this in the first video because of the geometric series. And now we're going to use this. So we want to find the power series and the interval of convergence for these functions. 1 over 1 plus x cubed. We are looking at a function and we want to find the power series. Well, we're going to use the function we already know. Basically, I want to make 1 over 1 minus x be the structure around this 1 over 1 plus x cubed. Making 1 over 1 plus x cubed look like 1 over 1 minus. I want a 1 over 1 minus. What has to be in these parentheses to get an x cubed, if I have a minus here, is a negative x cubed. This is h of x. This is that composition idea where I'm going to take the function and plug it in. Meaning 1 over 1 plus negative x cubed is equal to the series k equals 0 to infinity of thing inside those parentheses is the negative x cubed. Have that x and I have that x. That x has become a negative x cubed. And for our power series, we really like to rewrite it so that everything has the power. So this would be negative 1 to the k times x to the 3k. So distributing the k to both factors inside that parenthesis. So there is our power series, negative 1 to the k, x to the 3k, for 1 over 1 minus negative x cubed. And this should have been a minus here, but I wrote a plus. There's our power series. Now finding the interval of convergence is that 1 over 1 minus x equals the series from k equals 0 to infinity, x to the k, for the absolute value of x less than 1. This means I'm going to copy this all down, except leaving out the x part. What we've put in the x part is that negative x cubed. So negative x cubed is equal to that series for the absolute value of negative x cubed is less than 1. Solving out this inequality, it would be then the absolute value of x cubed is less than 1 because the negative goes away in the absolute value. And then taking the cube root, we still get x is less than 1. So the interval of convergence is still that absolute value of x being less than 1. So the interval didn't change. Again, the interval might change. The interval didn't. But the way we find it is by using the previous interval of convergence. Yeah. Now let's take a look at this other example. Is we have x over 27 minus x cubed. Once again, we want to make this look like the series 1 over 1 minus x. So we ultimately want to get the form of a 1 over 1 minus something. That's going to take a little bit of work. First, getting the x out of that numerator and making it a 1, I'm going to factor x out. So I have 1 over 27 minus x cubed. Next thing, I want to get the 27 out of this position in the denominator. So I'm going to factor 27 out. So I have x over 27, 1 over 1 minus factoring 27 out of that x cubed, I get x cubed over 27. And now I have the appropriate form. What's in the x position is that x cubed over 27. So I can plug that into the series. I'd have my series of x cubed over 27 to the k. But what we did to make this look like the power series is we factored out an x over 27. So we need that out front as well. From here, it's a rewrite of what we have. Distributing the k to everything, we'll have x over 27, series k equals 0 to infinity, x to the 3k over 27 to the k. And what property 2 tells us is just I can take that term and I can multiply it in. So that x over 27 is something I can multiply into the series, making the series the sum k equals 0 to infinity of x to the 3k plus 1 over 27 to the k plus 1. 27 times 27 to the k is 27 to the k plus 1. X times x to the 3k is x to the 3k plus 1. So there is our power series. I'm going to back up and do the interval of convergence now. And I'm going to use what we used before, but change out our numbers. So remember, 1 over 1 minus x is the series k equals 0 to infinity of x over k. We had the series x over 27 minus x cubed, which became x over 27 times 1 over 1 minus x cubed. And our series overall became, I'm going to leave the x over 27 out here, and it became x to the 3, or x cubed over 27 to the k. This converges for x cubed over 27 being less than 1. I could multiply this 27 in and have x to the 3k plus 1 over 27 to the k plus 1. But the same rules would apply to when we did geometric and we found the ratio. What we're putting in here is, what is that ratio? What is the thing that's all being raised to the k power? And what's being raised to the k power is the x cubed over 27. Working that out, multiplying everything by 27, we get x cubed is less than 27. Taking the cube root of 27 is 3, meaning x is between 3 and negative 3. So the new interval of convergence is negative 3 is less than x is less than 3. So we use our old series to find the interval of convergence by plugging in whatever we put in for x into the old interval of convergence. And one last example for this is, suppose we want to go the other way. Find the function represented by the series k equals 0 to infinity, x to the 2k over 9k, and find the interval of convergence. There's not a lot we can use here. The only series we know at this point is that x to the k is equal to 1 over 1 minus x. So if we know that information, we probably want to make this series look like x to the k. So x to the 2k over 9 to the k is the same as the series of x squared over 9 to the k. Well, x squared over 9 is in that position of x. So plugging it in, we'd have 1 over 1 minus x squared over 9. Now here is just a rewrite. I'm going to multiply everything by 9 to have 9 over 9 minus x squared. What is the interval of convergence? Well, this works for the absolute value of x being less than 1. So this works for, using that same trick, x squared over 9 less than 1. Multiplying by 9, we get the absolute value of x is less than 9. X squared is less than 9. And same as before, when I take the square root, I have the absolute value of x is less than 3. So our interval of convergence is negative 3 is less than x is less than 3. Now we had a lot of 1s and 3s. That does not mean those are the only options. Just means that was how these problems worked out. But we use the old series and function to find our properties about our new series and function. In the next video, we're going to take a look at integrating and differentiating power series.